What if I told you that this very moment, the one you are experiencing right now, isn't special? That somewhere in the vast four-dimensional fabric of the universe, the moment of your birth is still happening, and so is the moment of your death? What if our entire concept of time as a river flowing from past to future is just a grand, persistent illusion? Over the next 100 facts, we are going on a journey to dismantle everything you thought you knew about time. And our first stop is the biggest question of all. What is it? Let's start by shattering our most fundamental assumption. The truth is, according to many physicists, time doesn't actually flow at all. This is our first mind-bending fact. We perceive ourselves as moving from a fixed past through a fleeting present and into an unknown future. But a leading theory in physics, known as the block universe theory, suggests something far stranger. It proposes that time is a dimension just like the three dimensions of space: length, width, and height. In this model, the past, present, and future all exist simultaneously. They are all equally real, laid out in a static, four-dimensional block of space-time. Think of it like a movie reel. We only experience one frame at a time, creating the illusion of movement and progression. But the entire film, every frame from the beginning to the end, already exists. According to this view, the dinosaurs aren't gone. They're just in a different part of space-time. The future isn't unwritten. We just haven't arrived at that frame yet. This turns our entire life into a fixed object, a complete story that we are simply reading, one word at a time. It's a concept that challenges the very notion of free will, and it's the bedrock for understanding just how weird time truly is. If the entire timeline exists at once, that brings up a huge problem for the idea of now. And that leads us to our second fact. There is no universal now. We all feel like we share a single, simultaneous present moment with everyone else on Earth, and maybe even across the universe. But Albert Einstein's theory of relativity proved this is just not true. He realized that the speed of light is constant for all observers, which has a bizarre consequence. Simultaneity is relative. Imagine you're on Earth, and your friend is on a spaceship heading to Mars. If you both try to sync your watches, you'll find it's impossible to agree on what now is. An event that you see happening right now on Earth might, from your friend's perspective, have already happened or not happened yet, depending on their speed and direction. This isn't a trick of perception. It's a fundamental property of the universe. The faster your friend moves relative to you, the more out of sync your nows become. There is no master clock for the cosmos. Every single person, every planet, every galaxy has its own unique present moment. It's a lonely thought, but your now is exclusively yours. This idea that motion affects time isn't just theoretical, it's a verifiable physical law. Which brings us to our third astonishing fact. Time literally slows down the faster you move. This is called time dilation, and it's one of the most famous predictions of Einstein's theory. The closer you approach the speed of light, the slower time passes for you relative to a stationary observer. This isn't just your watch ticking slower. It's your body aging slower, your thoughts processing slower. Your entire reality is moving through time at a different rate. The classic example is the twin paradox. If one twin stays on Earth while the other travels in a spaceship near the speed of light for a year, upon returning, the spacefaring twin will be younger than the one who stayed home. This isn't science fiction. Astronauts on the International Space Station are moving at over 17,000 miles per hour. As a result, they are constantly traveling slightly into the future. After a 6-month mission, an astronaut will have aged about 0.005 seconds less than everyone on Earth. It's a tiny amount, but it's real, measurable, and it proves that speed is a functional time machine, even if it only works in one direction. But it's not just speed that has this godlike power over time. Gravity does too. And our fourth fact is one you use every single day without even realizing it. Gravity warps the flow of time. According to Einstein's theory of general relativity, massive objects don't just pull on things. They bend the very fabric of space-time around them, like a bowling ball on a trampoline. The stronger the gravitational field, the more space-time is curved, and the slower time passes. This means time moves slightly slower for someone standing on the beach than it does for someone on top of a mountain, because they are closer to the Earth's center of mass. The effect is minuscule, but with incredibly precise atomic clocks, scientists have measured it. Your head is actually aging ever so slightly faster than your feet. This isn't just a fun piece of trivia, it's essential for modern technology. The GPS satellites orbiting Earth are in a weaker gravitational field and are also moving very fast. Combined, these relativistic effects mean their internal clocks tick about 38 microseconds faster per day than clocks on the ground. If engineers didn't constantly correct for this gravitational and kinetic time dilation, your GPS would be off by about 7 miles every single day. So the next time you use Google Maps, you can thank Einstein for understanding that gravity doesn't just keep you on the ground, it changes time itself. So the universe has its own bizarre rules for time, but what about the clock inside our own heads? This brings us to a more personal truth, our fifth fact. Humans have an internal clock, and it is shockingly unreliable. Deep in our brains, in a region called the suprachiasmatic nucleus, we have a biological pacemaker that governs our circadian rhythms. But our perception of time passing is a completely different beast, influenced by almost everything. When you're having fun or are in danger, your brain releases dopamine and adrenaline, which seems to speed up your internal clock, making the external world appear to move in slow motion. That's why a thrilling moment can feel like it stretches on forever. Conversely, when you're bored, your brain is less stimulated and time seems to drag its feet. Age also plays a huge role. As we get older, our brains process new information less rapidly. For a child, a summer vacation feels like an eternity because it's filled with new experiences. For an adult, a year can fly by because so much of it is routine. Our perception of time isn't a reflection of objective reality, but a messy, subjective, and emotionally charged construction of our own minds. From the messy world of human perception, let's zoom out to the ultimate limit of precision. Fact number 6 is about the smallest slice of reality we can possibly measure. The shortest unit of time is called the zeptosecond. It is a staggeringly small number, a trillionth of a billionth of a second. To put that into perspective, there are more zeptoseconds in a single second than there have been seconds since the Big Bang. For a long time, scientists thought measuring anything on this scale was impossible. But in 2020, physicists were finally able to measure how long it takes for a photon, a particle of light, to cross a single hydrogen molecule. The answer was 247 zeptoseconds. This incredible measurement allows us to watch chemical bonds forming and breaking in real time, opening up a whole new frontier of quantum mechanics. It's the absolute mind-boggling speed limit of our ability to observe the universe, the fastest shutter speed imaginable. We've seen that time is a dimension, that it's relative, and that it can be measured with incredible precision. But what if our entire experience of it is just a quirk of our culture and language? Our seventh and final fact for this chapter is a profound one. The very concept of the future might not exist in some human languages. The Amandawa tribe, an indigenous community in the Amazon rainforest of Brazil, have a language that contains no abstract words for time, like month or year. They don't talk about events as being in the past or future. Instead of saying next week, they would refer to the next specific event, like after the next full moon. Their entire worldview is based on the immediate sequence of events, not a grand, abstract timeline. This suggests that our deeply ingrained feeling of time as a linear path we travel along might not be a universal human experience, but rather a conceptual framework we invented. It's a powerful reminder that our reality is shaped by the tools we use to describe it. Perhaps time isn't an external force we're all subject to, but a story we tell ourselves. A story that isn't the same for everyone. Have you ever felt that frantic, stomach-dropping panic when you realize you're late? That feeling is ancient. But for most of human history, the problem wasn't being 5 minutes late for a meeting, it was being an entire season late for a harvest. Before alarms, before watches, before the comforting tick-tock of a grandfather clock, how did humanity even begin to trap something as slippery as time? The answer wasn't found in a single invention, but in a desperate, brilliant, and sometimes bizarre quest to give the day a shape. This is the story of our very first clocks. The journey starts with the most obvious timekeeper we have, the sun. And that brings us to our 8th amazing fact about time. One of the first tools ever used to measure it was, quite simply, a stick in the ground. Known as a gnomon, this primitive device is the ancestor of all sundials. Around 3500 BC, the ancient Egyptians and Babylonians were already using them to track the movement of a shadow. They observed the shadow shortening as noon approached and lengthening as the sun began to set. It was a revelation. For the first time, the vast, formless expanse of daylight could be broken into smaller, manageable pieces. But it was the Egyptians who took it a step further, formally dividing the period of sunlight into 12 parts. These were the first hours, though they weren't the fixed 60-minute blocks we know today. An hour in the summer was much longer than an hour in the winter. It was a fluid, organic way of seeing time, tied directly to the rhythm of the sun itself. From a simple stick, humanity went big, really big. Which leads to a monumental fact. The iconic Egyptian obelisks were not just monuments to gods and pharaohs, they were colossal, city-sized clocks. These towering stone monoliths, some weighing over 400 tons, functioned as enormous gnomons. Their sharp, moving shadows would sweep across vast temple courtyards and public squares, marked with lines to indicate the time of day. They were public utilities, allowing anyone to glance up and gauge the hour. But they did more than that. The length of the shadow cast at noon changed predictably throughout the year, reaching its shortest point on the summer solstice and its longest on the winter solstice. So these stone giants were also calendars, marking the turning of the seasons and signaling the critical times for planting and for the flooding of the Nile. They were symbols of power that commanded not just space, but time itself. Of course, sundials and obelisks share a catastrophic flaw. When the sun goes down, or even just hides behind a cloud, you're completely blind to the time. This massive problem forced a brilliant leap in ingenuity, leading to one of the most important inventions in timekeeping history, the water clock. Known by its Greek name, the clepsydra, which literally means water thief, this device was a game-changer. The earliest examples, found in Egypt and Babylon around the 16th century BC, were simple stone vessels with a tiny hole near the bottom. You'd fill it with water, and as the water steadily dripped out, markings on the inside wall would show how much time had passed. It was the first reliable clock that worked at night, in any weather, indoors. This invention was so revolutionary that it was used for over 3,000 years. In ancient Athens, it found a crucial role in democracy. Court speeches were timed by a clepsydra. When the water ran out, your time was up. No exceptions. It was the ultimate, impartial judge, ensuring fairness by putting a strict limit on even the most powerful orator. But don't picture a simple dripping bucket. Some water clocks became mind-bogglingly complex mechanical marvels. In fact, for over 1,000 years, the world's most sophisticated timekeeping devices ran on water, not gears. In the 3rd century BC, the Greek inventor Ctesibius created a water clock with gears and a dial, featuring a pointer that tracked the hour and even adjusted for the changing length of days throughout the year. But the true masters were in the East. In the 11th century, the Chinese polymath Su Song constructed an astronomical clock tower that stood nearly 40 feet tall. It was powered by a giant water wheel and used a complex chain-drive mechanism. It didn't just tell the time, it had a rotating celestial globe that mirrored the sky, and automated, man-sized figures that would emerge from doors to clang bells and present plaques announcing the hour. It was less a clock and more an automated, water-powered cosmic cathedral. While water was king, it had its own Achilles heel. It freezes. In the colder climates of Northern Europe, a different solution was needed, and it came in the form of fire. This brings us to the candle clock, a simple but ingenious invention most famously associated with King Alfred the Great of England in the 9th century. Alfred was a devout and structured man who wanted to divide his day precisely, dedicating 8 hours to God, 8 to the affairs of his kingdom, and 8 to rest and study. To do this, his craftsmen created special candles made from a specific weight of wax, marked with 12 sections. Each candle would burn for exactly 4 hours, meaning each painted ring represented 20 minutes of past time. He kept 6 of these burning in succession, 24 hours a day, guarded within a lantern made of wood and translucent animal horn to protect the flame from drafts that could speed up or slow down the burn rate. It was a personal, portable, and surprisingly consistent way to bring order to a chaotic world. Following that same fiery logic, but with a fragrant twist, we find one of history's most beautiful timekeepers, the incense clock. Popular in China and Japan for centuries, these devices were a form of smokeless alchemy. They worked by burning a carefully prepared trail of powdered incense, often laid out in elaborate, maze-like patterns within a special tray. As the incense smoldered along its preset path, it marked the passage of time. But they were far more than simple timers. Different sections of the incense trail could be made from different aromatic formulas, so the scent in the room would literally change as the hours passed. In more advanced versions, small metal balls would be placed on the incense trail. When the smoldering line reached a certain point, the ball would drop onto a metal plate below with a crisp clang, marking the hour with sound. It was a clock that engaged multiple senses: sight, smell, and hearing. All of these inventions were about breaking down the day. But what about tracking the grand, celestial clockwork of the cosmos? In the year 1900, divers exploring an ancient Roman shipwreck off the coast of the Greek island of Antikythera found a lump of corroded bronze. For decades, it was dismissed as a rock or a piece of a statue. But when X-rayed in the 1970s, it revealed a stunning truth. Inside was a system of over 30 intricate, interlocking bronze gears. This was the Antikythera mechanism, an ancient device so complex it's often called the world's first analog computer. Dating back to the 2nd century BC, this shoebox-sized marvel wasn't a clock for telling the time of day. It was an astronomical calculator of breathtaking genius. By turning a hand crank, a user could perfectly predict the position of the sun, the moon, and the 5 visible planets. It could forecast eclipses and even showed the timing of the Olympic Games. The level of miniaturization and mechanical knowledge required to build it was thought to be impossible for another 1,500 years. It's a humbling reminder that our ancestors' understanding of time was, in many ways, far more advanced than we can possibly imagine. Shadows and water, fire and fragrance, and even a mysterious cosmic computer. For millennia, this was how humanity wrestled with time, using the elements to give it shape and meaning. Each method was brilliant, but each was flawed. They required constant attention, were subject to the weather, and lacked the one thing the modern world would come to demand above all else: precision. A new era was needed, an era driven not by the flow of water or the burning of wax, but by the cold, hard, reliable logic of a machine. The world was waiting for a new sound. It was waiting for the escapement, the pendulum, and the steady, relentless beat that would change everything. The revolution was coming, and it was about to tick its very first talk. Sound of a ticking clock, which abruptly distorts, slowing down with a low-pass filter effect, like a record slowing to a stop. Have you ever been in a near-miss car accident? That heart-stopping moment where a single second seems to stretch, unspooling into an eternity of detail? The squeal of the tires, the glint of sun on chrome, the wide eyes of the other driver, it all plays out in what feels like impossible slow motion. We've all felt it, that bizarre elasticity of time, the way it can drag during a boring meeting and vanish during a great conversation. But this isn't just a feeling, it's a profound neurological truth. Your brain doesn't just passively observe time, it actively creates it. And its version of now is one of the most wonderfully unreliable narrators you'll ever meet. So let's peel back the curtain on our own minds. This is where we get into our 15th amazing fact. Your brain warps time based on how surprising something is. It's called the oddball effect, and you can feel it yourself. Imagine a series of blue circles flashing on a screen, each for half a second. Blue, blue, blue. Then suddenly a red circle appears for the exact same half second. You would swear on a stack of physics textbooks that the red one stayed on screen longer. Why? Because novelty requires more brain power. Your brain dedicates extra neural resources to process the unexpected event. It's taking a more detailed snapshot, and that richness of information gets interpreted by your conscious mind as a longer duration. It's your brain's way of saying, "Whoa, hang on, pay attention to this, it's different." This simple trick is a cornerstone of how we experience the world, constantly stretching moments of surprise and compressing the mundane into an unremarkable blur. And this neurological editing doesn't stop there. Have you ever glanced at a digital clock right as the minute changes, or looked at an analog clock and felt like the second hand was frozen for a moment? That's not your imagination, and the clock isn't broken. It's a bizarre quirk of perception called chronostasis, and that's our 16th fact. Your eyes don't move in a smooth cinematic sweep. They jump around in rapid, jerky movements called saccades. To prevent you from experiencing the world as a nauseating, blurry mess during these jumps, your brain momentarily cuts off visual processing. It just goes dark for a few milliseconds. When your eyes land on the clock, your brain sees the new image, say 10:30:01, and to create a seamless experience, it cleverly backfills the time gap of the saccade with that image. It essentially lies to you, telling you that you've been looking at 10:30:01 for the entire duration of the eye movement, making that first second feel impossibly long. Your brain is literally rewriting your immediate past to make the present feel more stable. Of course, the most dramatic time bending of all happens when we're terrified. This brings us to fact 17. Fear doesn't actually make you see in slow motion, but it does create the powerful illusion of it. Neuroscientist David Eagleman famously put this to the test by having volunteers experience a 150-foot free fall into a net. They wore a special device that flashed numbers too quickly to be read under normal circumstances. The theory was, if their perception truly slowed down, they should be able to read the numbers. Not a single person could. So what's going on? It's all about memory. In a life-threatening situation, your amygdala, the brain's fear and emotion center, kicks into hyperdrive. It commands the rest of your brain to capture everything, every sight, sound, and feeling in the highest resolution possible. It creates an incredibly dense memory of the event. Later, when your brain plays back that memory, it's so jam-packed with data that you interpret the event as having taken much longer than it actually did. You don't get superpowers during a crisis, you just get a far better recording of it. But it's not just emotion and surprise that can warp our internal clock. Fact 18 reveals that your brain constantly confuses time with space, a phenomenon known as the kappa effect. Imagine sitting in a dark room with 3 lights in a row. The first one flashes, then the one in the middle, then the one on the end. If the distance between the middle light and the end light is much greater than the distance between the first 2, you will perceive the time between the last 2 flashes as being longer, even if the timing is perfectly identical. Your brain sees the greater distance and assumes it must have taken more time to cover it, literally stretching its perception of the seconds to fit the space. This happens in the real world too. A long, straight, boring stretch of highway can feel like it takes an eternity, while a winding, scenic road of the same length flies by, because the changing scenery breaks up the perceived space into smaller, more manageable chunks. And it gets even more physical than that. Our perception of time isn't just in our heads, it's in our blood. For our 19th fact, your internal clock is directly linked to your body temperature. We all have a biological pacemaker, a rhythm of neural firing that gives us our baseline sense of time. And like any chemical process, the speed of those neural firings is affected by heat. When you have a fever, your core body temperature rises, causing your internal clock to literally speed up. From your brain's perspective, the world outside seems to slow down to a crawl. This is why an illness can make an afternoon feel like a week. In experiments, people with induced higher body temperatures consistently overestimated the passage of time, judging a minute to have passed when only 45 or 50 seconds had actually elapsed. Your sense of now is, in part, regulated by your own internal thermostat. This biological link leads us to one of life's greatest mysteries, and our 20th fact, the reason time seems to accelerate as we get older. Scientists have a couple of powerful theories for this. The first is simple math. When you're 8 years old, a summer vacation is a huge portion of your entire life. It feels epic, endless. When you're 48, a summer is a tiny, almost trivial fraction of your lived experience, so it feels like it flashes by. But the more compelling explanation is about novelty. Your brain is a memory-making machine, but it's efficient. It doesn't like recording redundant information. Childhood is a constant stream of firsts. Your first bike ride, your first sleepover, the first time you see the ocean. Your brain is writing massive, detailed new files for these experiences. But as an adult, life settles into routines. The commute, the work week, the weekend chores. Your brain doesn't need to record these in high detail. It just updates the existing file. So, when you look back at the end of a year, there are fewer novel, richly detailed memories to anchor your perception of its length. The file is smaller, and so the year feels shorter. To slow down time, the secret is to constantly seek out new experiences. So, with time being pushed and pulled by novelty, fear, space, and even our body temperature, you have to ask, where is the master clock in our head that governs all this? And here's the mind-blowing finale for this chapter. Fact 21, there isn't one. Unlike vision, which is largely processed in the occipital lobe, or hearing in the temporal lobe, there is no single, dedicated time organ in the human brain. Instead, time perception is a distributed network. It's a group project between the cerebellum, which handles millisecond timing for motor control, the basal ganglia, which helps us feel rhythm and longer durations, and the prefrontal cortex, which pieces it all together into a coherent narrative. This decentralized system is precisely why our sense of time is so wonderfully fragile and easily influenced. Our experience of the present moment isn't a precise tick-tock from a Swiss watch. It's more like a complex piece of music being improvised by a dozen different parts of our brain at once. The now we feel isn't a measurement, it's a masterpiece of biological construction. What if you could leave Earth on a journey, travel at incredible speeds for what feels like only a year to you, and return to find everyone you ever knew was gone, that centuries had passed, and you had become a visitor in your own planet's distant future? This isn't the plot of a movie. This is a real physical possibility, and it's because our simple, everyday understanding of time is completely wrong. We've been living with a cosmic secret, one that was finally cracked open about a century ago, revealing that time isn't a steady, universal river. It's a raging, bending, and stretchable current that's different for every single one of us. Because, and here's our 20-second amazing fact, the faster you move through space, the slower you move through time. This isn't a metaphor, it's a fundamental law of the universe called special relativity, gifted to us by Albert Einstein. Imagine you have an identical twin. You stay on Earth while your twin blasts off in a spaceship that can travel near the speed of light. They zoom around the galaxy for, let's say, 5 years, according to the clock on their ship. But when they return to Earth, they'd be stunned. You wouldn't be 5 years older, you might be 50 years older, or 500. Time would have passed dramatically slower for the traveling twin. For them, only a few years went by. For you, decades or centuries could have elapsed. This is the famous twin paradox, and it proves that time is not absolute. It's relative to your motion. Every time you get in a car, on a plane, or even just go for a run, you are ever so slightly slowing down your personal clock compared to someone standing still. The effect is infinitesimally small in our daily lives, but it's always there, a constant reminder that we each have our own personal timeline. But speed isn't the only cosmic force that toys with time. Something far more massive, something you're feeling right now, is warping the flow of time all around you. Einstein wasn't done. He realized that gravity itself can bend the fabric of reality. Which brings us to our next fact: time literally runs slower in stronger gravitational fields. According to his theory of general relativity, massive objects like planets and stars don't just pull on things. They create a dip, a curve in the fabric of space-time. Think of it like placing a bowling ball on a giant rubber sheet. The sheet stretches and warps around the ball. Time, just like space, is part of this fabric. So the closer you are to that massive object, the deeper you are in its gravity well, the slower time will tick for you compared to someone farther away. This isn't just a theory we debate in classrooms, it's a crucial piece of our modern world. The GPS satellites orbiting Earth are in a weaker gravitational field than we are on the surface. Because of this, their internal atomic clocks actually run faster than ours by about 38 microseconds every single day. If scientists didn't constantly correct for this time warp, your GPS would be off by miles within hours, sending you driving into a lake instead of to the grocery store. And this gravitational slowdown isn't just for satellites. It is happening to you this very second in a bizarre and personal way. Believe it or not, your head is measurably older than your feet. Since your head is slightly farther away from the center of Earth's mass than your feet are, it's in a fractionally weaker gravitational field. This means time is ticking ever so slightly faster for your brain than it is for your toes. The difference is ludicrously small. We're talking a few nanoseconds over your entire lifetime, but it's real. Physicists with hypersensitive atomic clocks have actually measured this effect over a height difference of just 1 foot. So, every time you stand up, you are creating a tiny time differential across your own body. You are, in a very real sense, a walking, talking time machine, with your own personal past in your feet and your future in your head. If a little bit of gravity from our humble Earth can have such a strange effect, what happens when you introduce something with truly monstrous gravity? This leads to one of time's wildest twists. Black holes are theoretical time machines to the future. A black hole is so massive that its gravity well is practically a bottomless pit in spacetime. As you get closer to its edge, the event horizon, gravitational time dilation becomes extreme. If you could safely orbit a supermassive black hole without getting spaghettified, time for you would slow to a crawl compared to the outside universe. You could orbit for what feels like a few hours or days, then fly back to Earth. Upon your return, you wouldn't find a world a few days older. You would find a world that is thousands or even millions of years in the future. You would have taken a one-way trip, a shortcut through cosmic time, all by letting gravity do the heavy lifting. All this stretching and squeezing of time based on speed and gravity leads to an even more profound and unsettling conclusion. It utterly shatters an idea we all take for granted, the concept of now. The truth is, there is no universal now. The idea that we all share a single, simultaneous present moment across the universe is an illusion. It's called the relativity of simultaneity. At the exact moment, very fast train moving past a platform. At the exact moment the middle of the train passes you, 2 bolts of lightning strike the very front and the very back of the train simultaneously from your perspective on the platform. You see both flashes at the same time. But for a person sitting in the middle of that speeding train, the light from the front strike has less distance to travel to reach them, while the light from the back strike has to catch up. They will swear that the lightning hit the front of the train before it hit the back. So, who is right? You both are. Simultaneity, what happens at the same time, depends entirely on your frame of reference. This means an alien in a galaxy a million light-years away, moving relative to us, could have a now that corresponds to Earth's Jurassic period, or a now that is thousands of years in our future. The universe doesn't have a single agreed-upon present moment. So if time slows with speed, what happens at the ultimate cosmic speed limit? The speed of light itself? This brings us to a mind-melter. From a photon's point of view, time does not pass at all. A particle of light, a photon, experiences its entire journey, no matter the distance, in literally 0 time. Think about that. A photon emitted from the sun travels 93 million miles to reach your eye in about 8 minutes from our perspective. But from the photon's perspective, its creation at the sun and its absorption in your retina happen at the exact same instant. There is no travel time. A photon from the Andromeda galaxy embarks on a journey that, to us, lasts 2.5 million years. But for that photon, its birth in a distant star and its death on Earth are the same event, separated by no time whatsoever. It experiences the entire universe in a single, timeless flash. This all sounds like wild, speculative fiction. Time travel, aging heads, non-existent nows. It's easy to dismiss it as just mathematical quirks. But our final fact for this chapter grounds it all in absolute reality. We have directly measured these relativistic effects with astonishing precision. Back in 1971, In what's known as the Hafele-Keating experiment, physicists put hyper-accurate cesium atomic clocks on commercial airliners and flew them around the world, once eastward and once westward. When the planes landed and they compared the clocks to a reference clock that had stayed on the ground at the U.S. Naval Observatory, they found the clocks no longer agreed. The flying clocks were out of sync by a matter of nanoseconds, and the discrepancy matched the predictions of both special and general relativity, accounting for both their high speeds and their higher altitude, almost perfectly. They had proven definitively that you can travel into the future, even if it's just by a few billionths of a second. Every time you fly, you're doing it too, returning to the ground a tiny fraction of a second younger than you would have been if you'd stayed put. Einstein's ripples in time aren't just a theory, they're a proven, bizarre, and beautiful feature of our universe. Have you ever tried to slice a moment? I mean, really slice it. Take 1 second, cut it in half, then in half again. Keep going. How many times can you do it before you're left with something so small, so fundamental, that it simply can't be cut any further? We've journeyed through time on the cosmic scale, but now we're going in the other direction. We're zooming past the millisecond, the microsecond, the nanosecond, and diving headfirst into the bizarre, baffling realm of quantum mechanics, where the very ticking of the clock starts to break down. Because here, at the bottom of reality, we find that time itself has a smallest possible unit. It's a fact of the universe that there is a temporal pixel, a single frame in the movie of reality known as Planck time. It's equal to roughly 10 to the power of -43 seconds. Writing that number out would be a 0, a decimal point, followed by 42 more zeros, and then a 1. To give you some perspective, the time it takes for light to cross a single proton is a trillion times longer than 1 unit of Planck time. It is so incomprehensibly short that physicists believe it's the absolute limit. Any event or process that happens faster than Planck time is considered physically meaningless. It's the point where our understanding of cause and effect, of before and after, completely dissolves. Space-time, at this scale, is no longer a smooth fabric. It's a chaotic, bubbling foam of quantum probability. So the ultimate speed limit isn't just how fast you can travel in space, but how fast an event can even happen. From the fastest possible moment, let's jump to one of the most famously weird quantum behaviors, tunneling. This is the phenomenon where a particle, like an electron, can essentially teleport through a solid barrier it shouldn't have the energy to overcome. It's like throwing a tennis ball at a brick wall and having it just appear on the other side. For decades, a huge debate raged. Is this process instantaneous? Does the particle break the speed of light for an infinitesimal moment? The answer, it turns out, is no. And we know this because scientists have actually timed it. Using incredibly clever experiments, physicists have measured the time it takes for a particle to tunnel through a barrier. It's a mind-bogglingly small duration. We're talking attoseconds, or quintillionths of a second, but it is crucially, measurably greater than 0. Even the universe's greatest magic trick has to obey a cosmic speed limit. Time, it seems, insists on marching forward, even for particles that cheat their way through walls. But how on earth do you measure an attosecond? You can't use a stopwatch. You need a clock of almost unimaginable precision, which brings us to one of the most fundamental misunderstandings about how we keep time. We think of clocks as devices that measure the flow of time, but our most accurate clocks do something subtly different. Atomic clocks don't measure time, they count. At the heart of the international definition of a second is a specific type of atom, cesium-133. When you gently excite this atom with a microwave, its outermost electron flips its orientation in a process called a hyperfine transition. This transition happens with a regularity that makes the solar system look sloppy. And so we made a simple, profound decision. We officially defined 1 second as the time it takes for exactly 9,192,631,770 of these oscillations to occur. Your GPS, the internet, global financial markets, they don't run on the ticking of a cosmic clock. They run on the universe humming a very specific quantum tune and our ability to count the vibrations. These quantum counters are the most stable timekeepers humanity has ever created. So what happens when you pit this quantum perfection against the universe-bending predictions of Albert Einstein? You get one of the most beautiful confirmations of physics ever performed. We know from relativity that time runs slower for a faster-moving object and also runs slower in a stronger gravitational field. To test this, in 1971, physicists performed the Hafele-Keating experiment. They took several hyper-accurate cesium atomic clocks, synchronized them, and then put them on commercial jets that flew around the world twice. When the planes landed and the clocks were compared to the reference clock that stayed behind at the U.S. Naval Observatory, they were out of sync. The flying clocks had lost a few nanoseconds, an amount that matched the predictions of special and general relativity almost perfectly. This was breathtaking. The strange, abstract warping of space-time wasn't just some cosmic theory. It was a physical reality so potent it could slow down the fundamental ticking of atoms themselves. Relativity stretching and squeezing our quantum clocks is one thing. But what if quantum mechanics itself holds a way to essentially stop time in its tracks? This brings us to a bizarre and deeply counterintuitive idea known as the quantum Zeno effect. It's often summarized by the old saying, "A watched pot never boils." In the quantum world, this isn't just a saying, it's a literal phenomenon. Imagine an unstable radioactive atom, which, if left to its own devices, has a certain probability of decaying within, say, 1 minute. But what if you keep looking at it? What if you measure it every single second, asking, has it decayed yet? How about now? Now? The act of continuous observation, of constantly measuring its state, can force the atom to remain in its undecayed state. You are essentially resetting its internal clock over and over, preventing it from making the quantum leap into decay. By watching it, you are freezing it. It's a profound revelation that in the quantum world, the observer isn't a passive bystander. The very act of looking at reality can halt its progression, locking a piece of the universe in a single, unchanging moment. We've seen time become pixelated, we've seen it bent by gravity, and we've seen it frozen by observation. This all begs a terrifyingly large question. What if time isn't fundamental at all? In our everyday experience, time feels like the ultimate bedrock of reality, the river on which everything else flows. But some theories in quantum gravity suggest time is actually an emergent property. Think of it like this. A single molecule of H2O isn't wet. Wetness is a property that emerges from the interaction of billions of those molecules. Likewise, time might not exist at the most fundamental level. This idea finds support in one of physics' most enigmatic equations, the Wheeler-DeWitt equation, which attempts to combine quantum mechanics and general relativity. In its most common form, the variable for time, the letter t that appears in almost every other physics equation, is completely absent. The equation describes a static, timeless universe. In this view, the flow of time we experience is a consequence of the complex quantum entanglement between different parts of the universe, a sort of grand illusion created by our macroscopic perspective. From that dizzying philosophical cliff, let's come back to solid ground and to the absolute pinnacle of our time-telling technology. Because while physicists debate whether time is real, engineers have been building clocks that would make cesium atoms look like sundials. The most accurate clocks in the world today are known as optical lattice clocks. Instead of microwaves, they use incredibly stable lasers to probe atoms like strontium or ytterbium. The lasers create a perfect standing wave of light, like an egg carton made of photons, which traps thousands of atoms in place, preventing them from jiggling around and causing errors. These atoms oscillate hundreds of thousands of times faster than cesium, allowing us to slice the second into far finer increments. The result is a clock so precise it's difficult to even describe. The latest experimental clocks would not lose or gain a single second in over 30 billion years. That is more than twice the entire age of the universe. These devices are now so sensitive, they can detect the time dilation caused by lifting the clock just 2 centimeters higher off a table. They are no longer just clocks, they are space-time microscopes, new senses that allow us to perceive the subtle warps in reality all around us, and they are paving the way for a whole new understanding of the universe's deepest secrets. So, if time can stretch and shrink out there in the cosmos, what about the timekeeper we carry around inside our own heads? Because you don't need a spaceship traveling near the speed of light to experience time differently. You just need a body. Every living thing on this planet, from a blade of grass to you watching this screen, is governed by a silent, invisible, and profoundly powerful clock. And our next fact reveals where the central gear of this incredible machine is located. Fact 36. Deep inside your brain, sitting right above the spot where your optic nerves cross, is a tiny, densely packed cluster of about 20,000 neurons. It's called the suprachiasmatic nucleus, or SCN for short, and it's no bigger than a grain of rice. But don't let its size fool you. This little speck of tissue is the master conductor of your entire biological orchestra. It's your body's central clock, the ultimate timekeeper that dictates nearly everything you do without you even thinking about it. It tells you when to feel sleepy, when to be alert, when to get hungry, and even when your hormones should rise and fall. It generates its own, near 24-hour rhythm completely on its own. Scientists discovered that if you take SCN cells out of the brain and keep them alive in a petri dish, they will continue to fire in a rhythmic 24-hour cycle for weeks, a ghost beat of a day that no longer exists. This tiny nucleus is the reason you feel jet lag, and it's the tireless engine driving the daily ebb and flow of your very existence. But here's where it gets truly mind-bending. That grain of rice-sized master clock isn't the only timekeeping in your body, not even close. Fact 37. In reality, you are a walking, talking city of clocks. Virtually every single organ, from your liver and lungs to your heart and muscles, has its own internal, self-sustaining clock. Even individual cells have their own molecular timekeepers, ticking away in perfect harmony. Think of the SCN as the central clock tower, chiming loudly for the whole city to hear. The clocks in your liver, which control metabolism, listen for that chime. The clocks in your muscles, which manage energy use and repair, listen for it too. Every part of you is constantly checking the time with the master clock in your brain to stay synchronized. This is why eating a big meal at 3 a.m. feels so wrong. Your stomach's clock is saying, it's time to rest, while you're telling it, it's time to work. This system of a central clock coordinating trillions of peripheral clocks is one of the most elegant and complex timing systems in the known universe. So, how do these clocks actually work? What are the cogs and gears made of? For decades, this was a complete mystery. But a revolutionary discovery finally pulled back the curtain, and it's a fact that literally won the Nobel Prize. Fact 38. Your biological clock isn't mechanical, it's genetic. At the heart of every clock, in the SCN and in every cell, is a delicate feedback loop of what are literally called clock genes. Two key genes, named period and timeless, or PER and cry in mammals, produce proteins. Throughout the day, these proteins slowly build up in the cell's nucleus. As their concentration gets higher and higher, they eventually reach a tipping point where they act as a stop signal, blocking their own genes from making any more of them. It's like a thermostat reaching a set temperature and shutting off the furnace. Then, overnight, these proteins gradually break down, and as their levels fall, the genes are switched back on, starting the whole cycle over again. This elegant, self-regulating loop takes, you guessed it, almost exactly 24 hours to complete. It's a genetic hourglass, counting out the moments of your life, one day at a time. Now, an internal clock that just runs on its own would be useless. It would slowly drift out of sync with the actual world. It would be like a watch that loses a few minutes every single day. Pretty soon, it's telling you it's noon when the sun is setting. So, our clocks need a way to reset. And our next fact reveals the most powerful time setter in nature. Fact 39. The cues that our bodies use to synchronize our internal clocks with the external world are called Zeitgebers, which is German for time givers. While things like meal times and exercise can act as minor Zeitgebers, the undisputed champion, the one that has governed life for billions of years, is light. The SCN is strategically placed right near the optic nerves for this very reason. Specialized cells in your retinas detect the presence of bright, blue-spectrum light and send a direct signal to the SCN that says, "Hey, it's morning, reset the clock now." This is why looking at the blue light from your phone or computer screen late at night is so disruptive. You are essentially screaming, "Wake up!" at your master clock at the exact moment it's trying to prepare your body for sleep. It's like yanking the hands of your watch backward every single night. This battle between our internal, ancient clocks and our modern, artificial world leads to a fascinating and frustratingly common phenomenon. Fact 40. Most of us are suffering from a condition known as social jet lag. This isn't the jet lag you get from flying across time zones. It's the mismatch you experience every week between your body's preferred sleep schedule and the schedule demanded by your job, school, and social life. If your body naturally wants to sleep from midnight to 8 a.m., but your alarm clock forces you up at 6 a.m. for work, you're creating 2 hours of social jet lag. Then, on the weekend, you catch up by sleeping in until 10 a.m., shifting your clock in the other direction. This constant yanking of your internal clock back and forth has been linked to a host of health problems, because you're essentially forcing your body to fly from New York to Chicago and back again every single weekend without ever getting on a plane. Of course, the reason this affects people so differently is that not all of our internal clocks are wound the same way. Fact 41. Your personal preference for mornings or evenings, known as your chronotype, is largely hardwired into your genes. You're not a morning person or a night owl because you're disciplined or lazy. You're one because your genetic clock literally runs slightly faster or slower than average. Morning people, or larks, often have a biological clock that runs a bit shorter than 24 hours, so their cycle finishes earlier, making them feel alert in the morning and sleepy in the evening. Night owls, on the other hand, tend to have an internal cycle that's slightly longer than 24 hours, so their peak alertness and sleepiness happen later in the day. It's a fundamental biological trait, like eye color or height, and trying to force a night owl to be a happy, productive lark is like trying to force a cat to enjoy swimming. Want a clue to figure out exactly when your internal clock is preparing you for slumber? It's not about how tired your eyes feel, it's about temperature. Fact 42. One of the most powerful and reliable signals your biological clock sends is the daily rhythm of your core body temperature. About 2 hours before you naturally fall asleep, your core temperature begins to drop, hitting its lowest point around 4 a.m. This dip is a crucial signal that helps initiate sleep. This is also the secret behind why a warm bath or shower before bed can be so effective. It's not about the warmth itself making you sleepy. It's about the rapid cool-down period after you get out. As your body temperature quickly drops back to normal, it mimics the natural temperature decline your clock creates, effectively tricking your brain into thinking, it must be time for bed. And this incredible internal timing isn't just a fancy feature for humans and animals. It's a fundamental aspect of life itself. Fact 43. Plants have incredibly sophisticated circadian clocks too. A plant knows what time of day it is, even in a windowless room with constant light. The mimosa plant, for instance, opens its leaves to the sun in the morning and closes them at dusk. And it will continue to do so for days in total darkness, anticipating a sunrise that never comes. Plants use their internal clocks to optimize photosynthesis, to release scents at the specific time of day their pollinators are active, and to know when to flower. This internal sense of time is a deep, ancient piece of programming, a shared inheritance that connects every living thing, reminding us that we are all, in our own way, dancing to the quiet, relentless rhythm of a 24-hour day. But what happens when we try to measure time on a scale that dwarfs our daily cycles? When we look to the seasons, to the years, to the grand sweep of history itself? Well, that's when things get really interesting. Have you ever stopped to think about the fact that inside every single one of your cells, right now, there's a clock? It's not metaphorical. It's a physical, biological timer, counting down with every division, and it has an alarm that's already been set. This is the relentless, personal experience of time's arrow, and it's arguably the most profound mystery we all face. So, how does this unstoppable march actually work? Well, that brings us to a fundamental limit programmed into our very DNA. You see, at the end of each of our chromosomes are protective caps called telomeres. The best analogy is the little plastic tip on the end of a shoelace, an aglet. Just as that aglet stops the shoelace from fraying, your telomeres stop your crucial genetic code from unraveling every time a cell divides. But here's the catch. With each and every division, those telomeres get a little bit shorter. A tiny piece is lost. It's a planned obsolescence written into our biology. After about 50 to 70 divisions, those telomeres become critically short. The cell gets the message loud and clear. Stop. It can no longer divide. This is fact number 41, the Hayflick limit. It's the invisible ceiling on a cell's lifespan, and it's one of the primary drivers of aging. As more and more of our cells enter this non-dividing state, called senescence, we see the results in the mirror. Wrinkles, slower healing, a gradual decline. It is the ticking of that cellular clock made visible. So, if all our cells have this built-in countdown, does that mean we all age at the same rate? Does turning 40 feel the same for everyone's body? Not even close. This leads to a crucial distinction that scientists make, and it's our 42nd fact. Your chronological age and your biological age are two completely different things. Your chronological age is simple. It's the number of candles on your birthday cake. It's how many times the Earth has orbited the Sun since you were born. But your biological age? That's the real measure of how old your body is physiologically. It's determined by a whole host of biomarkers, like the length of those telomeres we just talked about, your cardiovascular health, your metabolic rate, and your levels of inflammation. A 50-year-old who exercises, eats well, and manages stress might have the biological age of a 35-year-old. Meanwhile, another 50-year-old with a tougher lifestyle could have the biological machinery of a 65-year-old. Genetics, diet, environment, stress, they all turn the hands of your biological clock forward or back, proving that time's arrow doesn't fly at the same speed for everyone. But what if you could do more than just slow that biological clock? What if you could smash it on the floor, reverse its gears, and send it spinning backward? For one humble creature, that's not science fiction. It is, quite literally, how it avoids death. Let's talk about the mind-bending fact number 43. The jellyfish Turritopsis dohrnii is biologically immortal. Here's how this impossible feat works. Like other jellyfish, it starts as a tiny larva, which eventually settles on the seafloor and grows into a polyp, a plant-like stalk. This polyp then buds off new, genetically identical jellyfish, which swim away to live their lives. But if that adult jellyfish gets old, physically damaged, or faces starvation, it does something that defies the laws of aging. It performs a biological U-turn. It sinks back to the ocean floor, its bell and tentacles retract and are absorbed, and its very cells transform, reverting all the way back to the polyp stage. It becomes a baby again. From that new polyp, a whole new jellyfish will eventually bud off and swim away. It retains its old memories, if you can call them that, but in a brand new body. Barring being eaten by a predator or wiped out by a disease, it can repeat this cycle forever. It has found the ultimate loophole in the contract of life and death. That jellyfish has mastered biological time travel. But we've talked about how time isn't just biological, it's physical. It's woven into the fabric of the universe. And according to Einstein, that fabric can be stretched and squeezed. Which means you don't need to be a jellyfish to slow down aging. You just need a really, really fast rocket. This is Fact 44. Thanks to time dilation, astronauts genuinely age slower in space than we do on Earth. This is the real-world outcome of the famous twin paradox. If one twin stays on Earth, while the other travels in a spaceship near the speed of light, their clocks will tick at different rates. For the traveling twin, time itself slows down. When they return to Earth, they will be physically and biologically younger than the twin who stayed behind. Now, the effect for real astronauts is minuscule, but it is 100% real and measurable. After astronaut Scott Kelly spent nearly a year on the International Space Station, he returned to Earth about 5 milliseconds younger than he would have been otherwise. His twin brother, Mark, who remained on the ground, aged just a tiny fraction faster. It's a small difference, but it's concrete proof that the speed of your personal time, the rate at which you age, is not an absolute constant. It's relative to your motion through the universe. So the universe can warp our experience of time, but our own minds are even better at it, especially when we look backward. Think about your entire life for a moment. What memories feel the most vivid, the most important, the most you? For the vast majority of people, the answer is the same, and it reveals a strange quirk in how we remember our own timeline. This is Fact 45. It's called the reminiscence bump, and it's the scientifically proven tendency for older adults to have the strongest and most numerous memories from their adolescence and early adulthood, typically from about age 10 to 30. If you graph a 60-year-old's memories over their lifespan, you don't see a steady decline. You see a huge bump during this period. Why? Because that's the time of firsts. Your first love, your first car, your first job, moving away from home, forming your core identity. The brain prioritizes novel, emotionally charged experiences, and this period of life is packed with them. These events become the anchor points of your life story. It's why the music you listen to as a teenager feels more important and emotionally resonant than almost any music that comes later. Your brain wasn't just listening, it was building the soundtrack to your identity. This bump shapes our past, but our perception of time's forward momentum also warps as we move through life. Have you ever heard an older person say, "The years just fly by now"? They aren't just being wistful. They are describing a powerful psychological reality. So, for our 46th fact, time genuinely feels like it speeds up as we get older. There are a couple of leading theories as to why. The first is about proportion. When you're 8 years old, a single year is a massive 1/8 of your entire existence. Waiting from one birthday to the next feels like an eternity. But when you're 8, a year is just a tiny 1/80th of your life. It's a much smaller slice of your total experience, so it feels like it flashes by in an instant. The other theory is about novelty. Childhood is filled with new experiences that force your brain to actively process and record information. But as we become adults, life often falls into a routine. The commute to work, the weekly errands, the predictable seasons. With fewer novel events to mark its passage, our brain compresses time when we look back. A year with only a few distinct memories will feel much, much shorter than a year filled with firsts. From the microscopic clock in our cells to the vast clock of the cosmos, aging is a fundamental story of time. For us, that story plays out over decades. But for some creatures, the chapters are so long they're almost impossible for us to comprehend. In the cold, dark depths of the North Atlantic lives the undisputed king of longevity among all vertebrates. Fact number 47 is the Greenland shark, which can live for over 500 years. These ancient, slow-moving giants are living time capsules. They grow at a rate of less than a centimeter per year and don't even reach sexual maturity until they're about 150 years old. Imagine waiting a century and a half to even start thinking about a family. Scientists have dated them by analyzing the proteins in the lenses of their eyes, and the oldest one they found was estimated to be at least 392 and possibly as old as 512. This means there are sharks swimming in the ocean today that were born before the United States was a country, before the Industrial Revolution, during the time of Shakespeare. They are a profound, living reminder that while our own clock may tick relentlessly forward, time's arrow can fly at wildly different speeds. Have you ever considered that right now, as you're listening to this, your head is aging faster than your feet? It's not a riddle, and it's not a metaphor. It's a literal, measurable fact of the universe. Time isn't the steady, universal clock we imagine it to be. Out here, in the grand cosmic theater, time bends, it stretches, it slows down, and it might have even had a beginning. We've explored time on a human scale, but now we're going cosmic, where the rules get wonderfully, mind-bendingly weird. Let's start right back with your head and your feet. This strange little truth is thanks to something called gravitational time dilation. Albert Einstein revealed that massive objects don't just pull on things with gravity, they actually warp and curve the very fabric of space-time around them. Think of it like placing a bowling ball on a trampoline. The heavier the object, the deeper the dent it makes. Because time is part of this fabric, it's affected by the curve. The stronger the gravity, the deeper you are in that gravitational well, the slower time passes. Since your feet are slightly closer to the Earth's massive center than your head, they are in a slightly stronger gravitational field. The effect is infinitesimal, a matter of nanoseconds over your entire lifetime, but it is real. Scientists have proven it with hyper-accurate atomic clocks. In fact, if GPS satellites didn't constantly adjust their internal clocks to account for the fact that time moves faster for them up in weaker gravity, the entire global positioning system would fail, accumulating errors of about 10 kilometers every single day. So that little blue dot on your map works because we know that time is not the same everywhere. From the tiny difference between your head and feet, let's scale this idea up to the most extreme gravitational object we know of, a black hole. Here, gravity is so immense that time dilation becomes not just measurable, but absolute. At the edge of a black hole, at a boundary called the event horizon, gravity is so powerful that the escape velocity is greater than the speed of light. For someone watching from a safe distance, anything that falls towards it would appear to slow down as it approached the edge. Its light would stretch and redden, and it would seem to get dimmer and slower, eventually looking as if it were frozen in time, plastered against the event horizon for all eternity. But for the object itself, or a person unlucky enough to be falling in, time would feel perfectly normal. They would cross that boundary in an instant, unaware that to the rest of the universe, their final moment had been stretched into infinity. It's a place where the flow of time, as we know it, effectively comes to a halt. So gravity can slow time down. But what about speed? This is the other side of Einstein's revolutionary coin, special relativity. It turns out, the faster you move through space, the slower you move through time relative to a stationary observer. This leads to the famous twin paradox. Imagine two identical twins. One stays on Earth, while the other blasts off in a spaceship traveling at, say, 99.9% the speed of light. For the traveling twin, the journey to a nearby star and back might take only a few years, according to their ship's clock. They've been eating, sleeping, and aging normally. But when they return to Earth, they'll find that decades or even centuries have passed. Their twin would be an old person or long gone. This isn't science fiction. It's a physical reality confirmed by countless experiments, most notably with subatomic particles called muons. These particles are created in the upper atmosphere and have an extremely short lifespan, so short they shouldn't have enough time to reach the Earth's surface. Yet we detect them all the time. Why? Because they are traveling so close to the speed of light that from our perspective, their internal clocks have slowed way down, extending their lives long enough to complete the journey. All this talk of time stretching and shrinking raises a fundamental question. How old is everything, really? If time is relative, how can we possibly put a number on the age of the universe? The answer is written in the oldest light in existence, the cosmic microwave background. This faint, uniform glow that fills the entire sky is essentially the afterglow of the Big Bang, the leftover heat from creation. It's like the universe's baby picture. By studying the tiny temperature fluctuations in this ancient light, cosmologists can wind the clock backwards, calculating the expansion rate of the universe with incredible precision. And the number they've arrived at is that the universe is approximately 13.8 billion years old. This isn't a guess. It's a figure derived from the echo of the universe's first moments, giving us a universal starting point for our cosmic chronology. Now, 13.8 billion years is a number so vast it's practically meaningless to the human mind. To make it comprehensible, astronomer Carl Sagan created a brilliant analogy called the cosmic calendar. If you compress the entire history of the universe into a single year, the Big Bang happens at the first instant of January 1st. On this scale, our own Milky Way galaxy doesn't even form until May. Our solar system and Earth are late arrivals, showing up in early September. The first life on Earth appears around September 21st. The dinosaurs, those supposed masters of the ancient world, don't appear until Christmas Eve, December 24th, and are wiped out on December 30th. And humanity? All of our recorded history, every king, every empire, every war, every invention from the pyramids to the smartphone, occupies only the last 10 seconds before midnight on New Year's Eve. The life of an average person is but a fraction of a second. This calendar gives us a profound sense of humility, but it also prompts another question. If the clock started on January 1st with the Big Bang, what happened before? What was there on December 31st of the previous year? The mind-breaking answer might be that the question itself doesn't make sense. According to our current understanding, time itself began with the Big Bang. Physicists talk about something called Planck time, which is the smallest possible measurement of time that has any meaning, about 10 to the power of -43 seconds. In the very first instant after the Big Bang, before even 1 unit of Planck time had passed, the laws of physics as we know them, including general relativity and our very concept of time, completely break down. The conditions were so extreme that the notion of before may be as nonsensical as asking what's north of the North Pole. Time didn't exist in something. It began with everything else. From time's potential beginning, we arrive at one of its deepest mysteries, its direction. Why does time seem to flow in only one direction? You can remember the past, but not the future. An egg can scramble, but it can't unscramble. This one-way street is known as the arrow of time, and physicists believe it's inextricably linked to a concept called entropy. Entropy is, in simple terms, a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy can only increase. The universe as a whole is constantly moving from a state of low entropy, the highly ordered, hot, dense state right after the Big Bang, towards a state of maximum entropy, or complete disorder. This relentless, irreversible march towards chaos is what gives time its forward momentum. It's the universe breaking its egg, and it can never go back. It's this cosmic principle that ensures the clock ticks forward, not backward, carrying us from one moment to the next into an ever more disordered future. So, we've looked at the physics of time, the biology of time, even the psychology of time. But what if I told you the single biggest factor determining your relationship with time is your passport? Imagine showing up for a dinner party at 8 p.m. In Germany, you're insultingly late. In America, you're fashionably on time. In Brazil, you're so early the host is probably still in the shower. This isn't about being rude or polite, it's about running on entirely different cultural software. And that brings us to our next incredible fact. Many cultures operate on one of two invisible timelines, monochronic or polychronic. If you live in a monochronic culture, like the United States, Switzerland, or Japan, you see time as a single, tangible line. Monochronic cultures treat time like a resource that can be spent, saved, wasted, and lost. One thing at a time. Schedules are sacred. Interruptions are a crisis. The goal is to stick to the plan, but in a polychronic culture, common in Latin America, the Middle East, and much of Africa, time is a vast, swirling ocean. Punctuality is less important than relationships. Plans are just a suggestion, a rough sketch of what might happen. Juggling 5 conversations and 3 tasks at once isn't chaos, it's just living. An American manager in Mexico might be driven mad by employees who drift in late but stay long after closing to build relationships. To the manager, they're wasting company time. To the employees, they're investing in the human connections that actually make the business work. Neither is wrong. They're just speaking a different language of time. But what if the language you literally speak could rewire your brain for the future? This is one of the most debated and fascinating ideas in linguistics. Some languages are future tensed, like English, where we have a distinct way of saying, "It will rain tomorrow." Other languages, like German, Finnish, or Chinese, are often futureless. They can talk about the future, of course, but they tend to do it using the present tense, like saying, "Tomorrow it rains." It's a subtle difference, but economist Keith Chen discovered something staggering. Speakers of futureless languages are statistically more likely to save money, less likely to be obese, and practice safer sex. The theory, known as the futureless language hypothesis, suggests that if your language grammatically lumps the future in with the present, your brain perceives the future as being much closer and more connected to your current reality. Saving money doesn't feel like depriving your present self for some abstract future self. It just feels like moving resources around in the now. The future isn't a foreign country. It's just a different part of town. The debate is ongoing, but it suggests the grammar your parents taught you might be having a quiet but powerful conversation with your bank account. This link between language and time gets even stranger. For most of us, there's a universal metaphor. The future is ahead of us, and the past is behind us. We look forward to the weekend and put the past behind us. It just makes sense. You can see what's coming, right? Well, not for everyone. Deep in the Andes, the Aymara people have a completely inverted view. For the Aymara, the past is in front of them and the future is behind them. They're liable. The past is what you have seen with your own eyes, so it lies in your field of vision, in front of you. The future, being unknown and unseen, is behind your back. When they talk about next year, they often gesture over their shoulder, into the space they cannot see. It's a breathtaking piece of cognitive activity, proving that one of our most fundamental concepts, the direction of time's arrow, isn't a universal truth, but a cultural invention. So, if language can flip time backwards, can it erase the concept altogether? Well, not quite, but it can radically reshape it. Take the Hopi people of northeastern Arizona. In the 1940s, a linguist named Benjamin Lee Whorf made the explosive claim that the Hopi language contained no words, grammatical forms, or expressions that referred to what we call time. The Hopi language doesn't treat time as a measurable, flowing substance, but as a process of becoming. They don't say, "I stayed for 5 days." Instead, their grammar frames it more like, "I left on the 5th day." Whorf's initial claims were a bit exaggerated. They can, of course, talk about yesterday and tomorrow. But the core insight remains powerful. For them, time isn't a highway you travel along or a river that flows past you. Instead, the universe is constantly in a state of getting later. There isn't a noun called time, but a dynamic, unfolding event. You can't waste it or save it any more than you can waste or save the process of a plant growing. It simply is. This idea that time has different modes, different flavors, isn't just a modern linguistic discovery. The ancient Greeks were masters of this. We inherited our clock-obsessed view of time from them, but we only got half the story. The ancient Greeks had 2 distinct words for time, chronos and kairos. Chronos is the one we know. It's quantitative, linear, measurable time. It's the ticking of a clock, the sequence of events, the minutes on your calendar. It's the root of words like chronology and chronological. But they also had kairos. Kairos is qualitative time. It's the opportune moment, the perfect instant to act. It's not about the duration, but the significance. You can have hours of chronos and accomplish nothing, or you can seize a single second of kairos and change your life. Chronos is booking a meeting for 2 p.m. Kairos is the flash of inspiration you have in that meeting. Our modern world is drowning in chronos, efficiency, schedules, deadlines, while we're often starved for kairos, the moments of meaning. Our obsession with filling every moment of chronos leads to another cultural divide. In the West, a pause in conversation is often seen as awkward. A silent minute in a business meeting is excruciating. We rush to fill the void. But in other cultures, the void is where the meaning is. This brings us to the beautiful Japanese concept of ma. In Japan, kan, represents the pause, the interval, the empty space between things, and it is considered just as important as the things themselves. It's the silence between the notes that makes the music powerful. It's the unpainted space on a scroll that draws your eye to the subject. In conversation, ma is a deliberate, meaningful pause that allows for reflection and shows respect. It isn't an absence of content, it's a part of the content. While a Westerner might interpret that silence as disagreement or confusion, a Japanese person understands it as a moment of consideration. It's a profound reminder that time isn't just about what we do, but also the moments we choose to do nothing at all. From the pregnant pause to the pinnacle of punctuality. We started this journey with the idea of being late for a party, and we're going to end it with a culture that has elevated Chronos to a national art form. You might think of it as a stereotype, but the reality is even more intense. We're talking about Swiss trains. In most of the world, a train that arrives 5 or even 10 minutes late is considered on time, but not in Switzerland. There, the obsession with precision is baked into the national identity. 64. The Swiss Federal Railways officially defines a train as on time only if it is less than 3 minutes late, and in 2021, 91.9% of their passenger trains met this standard. This isn't just about efficiency, it's a cultural value of mutual respect. To be on time is to respect the time of every other person on the train, the station, and in the entire system. Their timetables are calculated down to the half-minute, and the entire national system is designed so that trains arrive and depart at key hubs at the same time, allowing for seamless transfers. It's a breathtakingly complex dance where every second counts, proving that while time might be a fluid, cultural story, some cultures choose to write that story with a stopwatch. What if I told you that you are a time traveler? Right now, and you have been your entire life. It sounds like a line from a science fiction movie, but it's the absolute truth. In our journey through the strangest facts about time, we've bent it, stretched it, and watched it slow down. But now, we arrive at the ultimate question, the one that has captivated humanity for centuries. Can we become masters of time itself? Can we visit the past or leap into the future? Let's find out. You see, we are all hurtling through time, experiencing it at a steady, reliable rate of 1 second per second. This forward march is the most fundamental and undeniable form of time travel there is. You're doing it right now, moving from the moment you started this sentence to the moment you're in now. But here's where it gets weird. That rate isn't quite the same for everyone. As we learned from Einstein, both speed and gravity can warp the flow of time. Astronauts aboard the International Space Station, for instance, are traveling at over 17,000 miles per hour. This incredible velocity, combined with the slightly weaker pull of gravity they experience in orbit, means their clocks tick just a fraction of a second slower than ours on the ground. When they return to Earth after a 6-month mission, they are about 0.007 seconds younger than they would have been if they'd stayed home. They have literally, physically, traveled a tiny fraction of a second into our future. It's not much, but it's proof of concept. The universe not only allows time travel, it mandates it. So traveling into the future by milliseconds is a proven fact. But what about taking a real leap? Could you visit the year 3000? According to the very same principles of physics, the answer is a resounding yes. It's just an engineering problem, a mind-bogglingly difficult one, but an engineering problem nonetheless. This is the domain of special relativity and a phenomenon called time dilation. The faster you move through space, the slower you move through time relative to a stationary observer. Imagine hopping on a spaceship that could accelerate to 99.995% the speed of light. You fly out to a star system 25 light-years away and then turn around and come back. For you on the ship, the journey would feel like it took about 1 year. But when you step back onto Earth, you'd find that a full 50 years had passed. Your friends would the world would have changed dramatically, and you would have successfully traveled 49 years into the future. Crank that speed up even closer to the light barrier, and the effect becomes exponentially more extreme. A trip to the center of our galaxy and back might take the astronaut a few decades, but they'd return to an Earth tens of thousands of years in the future.
Forward time travel isn't a fantasy. It has a clear scientific blueprint based on the fundamental laws of our universe.
Okay, so the future is theoretically open for business. But let's be honest, that's not the destination most people are dreaming of. The real prize, the holy grail of time travel, is the past. And that's where things go from being an engineering problem to a logical nightmare. The moment you consider going backward, you slam headfirst into a wall of paradoxes. The most famous, of course, is the grandfather paradox. Let's say you build a time machine, travel back to the 1950s, find your own grandfather before he met your grandmother, and accidentally cause him to say, trip, and miss the bus where they were fated to meet. They never get together. Your parent is never born, and consequently, you are never born. But if you were never born, how could you have gone back in time to interfere in the first place? The entire chain of events unravels itself. It's a causal loop that breaks logic, and it's not the only one. There's the bootstrap paradox, where an object or a piece of information has no origin, like taking a copy of Hamlet back to Shakespeare and having him publish it, leaving the question, who actually wrote Hamlet? These logical contradictions are so profound, they suggest backward time travel might be fundamentally forbidden. But physics is notoriously clever at finding loopholes. And the most popular theoretical loophole for a trip to the past has a suitably sci-fi name, a wormhole. Officially known as an Einstein-Rosen-bridge, a wormhole is a hypothetical shortcut through the fabric of spacetime. Imagine spacetime is a giant sheet of paper. To get from one side to the other, you have to travel across the surface. But a wormhole would be like folding the paper in half and poking a pencil straight through, creating a tunnel connecting two distant points in space and potentially in time. How? Well, if you could create a stable wormhole, you could leave one end of it stationary and take the other end on a trip at near light speed. Thanks to time dilation, the moving end would age slower. So you could end up with one mouth of the wormhole here on Earth in the year 2050, while the other mouth is still back in 2025. Step through one way, you're in the past. Go the other way, you're back in the future. The catch? It's a huge one. We've never observed a wormhole, and our theories suggest they would be subatomically small and collapse in an instant. To hold one open, you'd need a hypothetical substance called exotic matter, which possesses negative mass. We have no idea if such a thing can even exist. So if cosmic tunnels are out, what else is there? Believe it or not, Einstein's own theory of general relativity contains other, even stranger possibilities. The equations that describe how gravity curves spacetime actually permit solutions called closed time-like curves, or CTCs. These are exactly what they sound like: paths through spacetime that loop back to their own starting point in time. If you could navigate your spaceship along a CTC, you would travel through space and arrive back where you began, but before you left. It's the ultimate scenic route. Theoretical physicist Frank Tipler proposed that an infinitely long, massive cylinder spinning at nearly the speed of light could create such curves around it. Another potential location for CTCs is within the chaotic region just beyond the event horizon of a specific type of spinning black hole. Of course, both of these scenarios require conditions so extreme, infinite cylinders or surviving a trip inside a black hole, that they remain firmly in the realm of mathematical curiosity rather than practical possibility. Still, it's astonishing that the math doesn't say no. With all these paradoxes and impossibilities piling up, it seems like the universe is fighting hard to protect its history. But what if the universe has a get-out-of-jail-free card? A mind-bending idea from the world of quantum mechanics might just solve everything. The many worlds interpretation. This theory suggests that for every possible outcome of any event, the universe splits. There isn't just one timeline. There's an infinite canopy of branching timelines. This completely reframes the grandfather paradox. If you go back in time and prevent your grandparents from meeting, you don't erase yourself from existence. Instead, your action cleaves off a new branch of reality, creating an alternate timeline where you were never born. Your original timeline, the one you came from, remains perfectly intact and unchanged. You are now simply a visitor, an anomaly in this new parallel universe you've just created. In this model, you can't change your own past. You can only create a new one and abandon your old one forever. No paradox, just endless possibilities. This all sounds thrilling, but it leads to a very simple, very powerful observation. One that doesn't require complex math, just a look around. This final fact is perhaps the most compelling argument against backward time travel ever conceived. It's the unsettling silence. The late, great Stephen Hawking put it best when he formulated his chronology protection conjecture, the idea that the laws of physics must somehow prevent time travel to the past. His evidence was simple. If time travel into the past was or ever will be possible, where are all the tourists from the future? Why aren't our museums filled with historians meticulously documenting events as they happen? Why haven't lottery winners appeared from tomorrow? Their complete and total absence is a deafening one. It suggests that for all our brilliant theories, for all the loopholes in relativity, there might be a fundamental, unbreakable law we have yet to discover. A law that ensures that the past remains where it is, untouchable. Upbeat, mysterious music begins with a subtle ticking clock sound effect. Imagine you're standing at a crossroads, left or right. That's it. You choose left. You walk down that path, meet new people, have new experiences, and your life unfolds. But have you ever had that nagging feeling? What if I'd turned right? In the world we're about to explore, that isn't a what if, it's a what is. That other you, the one who turned right, is just as real as you are. We've been journeying along a single river of time, but now we're about to discover that this river may be just one tributary in an infinite cosmic ocean of parallel presence. This brings us to one of the most staggering ideas ever conceived in physics, a concept that completely shatters our idea of a single reality. The many worlds interpretation, or MWI, proposes that the universe is constantly splitting into parallel versions of itself. First proposed by physicist Hugh Everett III in 1957, it was his solution to a bizarre quantum problem. See, on a subatomic level, particles like electrons exist in a fuzzy cloud of probabilities, a superposition, until they're measured. When measured, they snap to one definite state. The old interpretation said the other possibilities just vanished. Everett asked a simple yet revolutionary question. What if they don't vanish? What if, at the moment of measurement, reality itself cleaves in two? In one universe, the particles spun up. In another, a brand new, equally real universe, it spun down. Every quantum event, from a radioactive atom decaying to a photon hitting your eye, fractures the cosmos. This isn't just happening in a lab, it's happening everywhere, all the time, creating a near-infinite, ever-branching tree of universes. There's a universe where you wore a different shirt today, a universe where you pursued that childhood dream, and a universe where the dinosaurs never went extinct. It's natural to hear that and think, okay, but we're in the real one, right? The others are just echoes. But that's our ego talking. The theory makes a chilling clarification. 75. In the many worlds model, there is no main or original timeline. Our universe holds no special status. It's not the trunk of the cosmic tree. It's just one tiny twig on one of trillions of branches. Every single diverging reality is as physically real and valid as our own. The you in this reality feels just as authentic as the you in a dozen others. To them, you are the alternate timeline. This completely decentralizes our place in the cosmos, suggesting that reality isn't a single story, but an infinitely large library with every possible book on its shelves, and we just happen to be reading one of them. This idea has some truly unsettling consequences when you apply it to life and death. It leads to a mind-bending thought experiment that sounds like something out of a horror film, but is a direct logical consequence of the many worlds theory. It's called quantum suicide. According to the logic of quantum immortality, your consciousness would never experience its own death from a random event. Imagine a grim scenario. You are in a room with a gun pointed at your head. The trigger is connected to a quantum measurement device. If a particle is measured spinning up, the gun fires. If it spins down, it just clicks. From an outside observer's perspective, it's a 50-50 shot. But from your perspective, the universe must split. In one branch, you die. In the other, you live. The critical part is this. Your consciousness, your stream of awareness, cannot continue in the universe where you die. It can only continue in the universe where the gun clicked. So you pull the trigger. Click. You do it again. Click. Again and again, 1,000 times. To the outside world, you died on the first try in 50% of worlds. But to you, you are seemingly immortal, always finding yourself in the reality branch where you survived. You would only ever be aware of the outcomes that allow you to remain aware. The many worlds theory is about endlessly branching, diverging timelines. But it's not the only multiverse model on the table. Other theories get even stranger. Let's go back to the block universe idea for a moment. The theory that all of time, past, present, and future, already exists simultaneously in a static 4D block. Instead of one timeline branching, some theories suggest entirely separate block universes could exist parallel to each other. Think of our entire cosmic history, from the Big Bang to the final heat death, as a single solid loaf of bread. A parallel universe would simply be another loaf of bread sitting next to ours on a cosmic shelf. It doesn't branch from ours. It has its own unique, self-contained history, its own laws of physics, and its own timeline laid out from start to finish. There could be an infinite number of these blocks, each a complete and separate reality, existing in a larger, unknowable hyperspace. And if those other cosmic blocks exist, would time even flow the same way? Our sense of time's direction is deeply connected to a fundamental law of physics, entropy, the tendency for systems to become more disordered. 78. In a parallel universe, the arrow of time could potentially run backward or not exist at all. Our universe began in a highly ordered, low entropy state after the Big Bang, and it has been getting more chaotic ever since. This increasing entropy is what gives us a distinct past and future. But what if another universe was created in a state of maximum chaos? In such a universe, entropy couldn't increase, and there would be no thermodynamic arrow of time. Time might feel like a directionless space. Or, stranger still, a universe could exist where entropy is decreasing, where shattered eggs reassemble themselves and smoke flows back into a fire. From our perspective, its time would be running completely in reverse. This all sounds like the perfect setup for interdimensional travel, right? Hopping between universes to see one where time runs backward. Unfortunately, the physics that allows for these worlds also seems to build a firewall between them. The principle of quantum decoherence likely makes communication or travel between these parallel universes impossible. When a universe splits in the many worlds model, the different versions decohere.
Their quantum wave functions become so out of sync with each other that they can no longer interact in any meaningful way. They become causally isolated, sealed off from one another forever. This is the universe's way of keeping its bookkeeping clean. All possibilities can happen, but they can't peek at each other's notes. So, while a version of you who is a rock star might exist, you'll almost certainly never get to meet them. But there is one final spectacular theory of parallel worlds that hints at a much more violent and interactive cosmos. It comes from the cutting edge of M-theory, an extension of string theory. 80. The brain world theory suggests our entire universe is just a three-dimensional membrane, or brain, floating in a higher dimensional space, and it could collide with other universes. Imagine our universe as a single sheet of paper floating in a room. That room is a higher dimensional reality called the bulk. According to this theory, the room is filled with other floating sheets of paper, other brain universes. Most of the time, they just float past each other, but sometimes they could collide, and the energy released from the collision of two entire universes would be titanic, more than enough to trigger a Big Bang. This provides a mind-blowing potential answer to the question of what came before our own time began. It might have been the cataclysmic impact of our universe with another, older one, resetting the cosmic clock and birthing our timeline as we know it. Our entire history of time, in that case, wouldn't be a beginning, but just the latest chapter in an endless cosmic demolition derby. Upbeat, mysterious music begins, then fades slightly to a background hum. What if I told you the most profound question you could ask about time is also a trick question? For centuries, we've stared at the stars and wondered what happened before the Big Bang. It seems like a simple, logical query. But asking it is a bit like standing at the North Pole and asking, which way is north from here? The question itself breaks down because the very concept of north starts right where you're standing. In much the same way, our journey to the ultimate origin story reveals that the concept of before might just be an illusion. We've explored time's grip on our lives, its strange behavior near black holes, and its potential for travel. Now we go to the very edge of existence itself, to a time before time. And that brings us to a fundamental misunderstanding many of us have about the universe's grand opening. We often imagine a single point exploding in a vast, dark, empty space. But according to the standard model of cosmology, the Big Bang wasn't an explosion in space. It was the beginning of space and time itself. There was no pre-existing void for it to expand into. The singularity, that infinitely dense and hot point, contained everything, all the matter, all the energy, and even the dimensions we inhabit. When it began to expand, it wasn't filling a container. It was the container, stretching and creating the fabric of space-time as it went. Every point in our universe today was once part of that initial singularity. So technically, the Big Bang happened right where you are sitting, and everywhere else, all at once. There was no outside for it to happen in, and no before for it to happen after. This idea that time has a definitive starting point isn't just a modern scientific concept. In fact, long before Einstein and Hubble, the 4th century philosopher Augustine of Hippo argued that time was created with the universe, not before it. People would ask him, what was God doing before he made heaven and earth? Augustine's brilliant answer was that the question was meaningless. He reasoned that God exists outside of time. Therefore, God created the universe and time simultaneously. There was no before because time itself is a property of the universe. He famously wrote, "The world was made not in time, but with time."
It's a stunning piece of philosophical insight that predates the scientific theory of space-time by over 1,500 years, showing how humanity has wrestled with this same cosmic riddle across millennia. But as we push our modern physics to its absolute limits, we can peer back to the briefest conceivable moment after creation. This is the Planck epoch, and it represents the smallest measurable unit of time at the dawn of the universe, lasting for just 10 to the minus 43 seconds. That's a decimal point followed by 42 zeros and then a 1. It's a slice of time so incomprehensibly short that our current laws of physics, including general relativity and quantum mechanics, completely break down. During this epoch, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have been unified into a single superforce. The universe was smaller than a subatomic particle, yet contained all the energy it would ever have. We can't describe what happened during this moment. It's a wall beyond which our science cannot currently see. The Planck epoch isn't just the first tick of the cosmic clock. It's the point where the very concept of a clock dissolves into a quantum fog. But what if the Big Bang wasn't a beginning at all, but just a turning point? This is where we enter the mind-bending territory of the Big Bounce. One of the leading alternative theories suggests that our universe could be part of an endless cycle of expansion and contraction, meaning our Big Bang was preceded by the collapse of a previous universe. In this model, the universe expands for trillions of years until gravity eventually halts the expansion and pulls everything back together. It all collapses down into an incredibly dense state, not quite a singularity, and then bounces, triggering another Big Bang and a new universe. If this is true, then time didn't begin 13.8 billion years ago. It has no beginning and no end. It's an eternal cosmic breath, inhaling and exhaling universes over and over. Asking what came before our Big Bang would just lead you to the end of the last universe in the chain. And incredibly, there might be faint echoes of this previous cosmic life hidden in plain sight. Scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, have found strange anomalies that don't quite fit the standard model. One of these, controversially nicknamed the axis of evil, is a strange alignment of patterns in the cosmic heat map. Some physicists, like Roger Penrose, have proposed that circular patterns and cold spots in the cosmic microwave background could be the remnants of black hole collisions from a previous cosmic aeon. According to his theory, the end of one universe, after all its black holes have evaporated, smoothly transitions into the Big Bang of the next. These faint circles in the sky could be the ghosts of a long-dead cosmos, providing tantalizing, though heavily debated, evidence that we are not the first universe, just the latest in an infinite series. Stepping away from cycles, another popular theory suggests our universe isn't alone, but is just one bubble in a vast, frothing sea of other universes. This is the theory of eternal inflation. It posits that while inflation, the rapid expansion of the early universe, stopped in our cosmic neighborhood, it continues raging on in a wider expanse, constantly birthing new bubble universes. So, the Big Bang might not have been a unique event, but simply the moment our pocket universe branched off from an eternally inflating multiverse. In this scenario, the multiverse as a whole may have existed forever. Time didn't begin with our Big Bang. Our particular timeline simply started then. Each bubble universe could have wildly different physical laws, different dimensions, and a different experience of time itself. It transforms the Big Bang from the creation event into just a creation event. Perhaps the most elegant and baffling idea for dealing with the before problem comes from the late great Stephen Hawking.
In his no-boundary proposal, he and James Hartle suggested a radical new way to look at the universe's origin. They proposed that if you travel back to the Big Bang, the distinction between time and space disappears, meaning the universe has no definitive starting point. Think of it like walking on the surface of the Earth. As you head south, you can eventually reach the South Pole. But once you're there, you can't go any further south. The direction itself ceases to exist. Hawking proposed that time behaves in the same way. As you approach the Big Bang, time's arrow smoothly transforms into another dimension of space. The universe didn't erupt from a single point in time because the very concept of time gives way to a smooth, curved, four-dimensional space. There is no sharp edge, no boundary, and therefore no moment of creation to ask what came before. The universe, in this view, simply is, without a beginning. This leads us to one final, perfectly symmetrical, and truly wild idea. If time and space are so deeply connected, what if the Big Bang wasn't just a beginning, but a central point? A recent theory proposes that the Big Bang may have created two universes, our own, moving forward in time, and a mirror universe on the other side, moving backward in time. From our perspective, their time is running in reverse. From their perspective, our time is. For both universes, the Big Bang is their common past, the origin point from which their cosmic clocks started ticking in opposite directions. This model neatly explains some cosmological puzzles, like the nature of dark matter, and presents a universe that is perfectly symmetrical in time. It means that the instant of creation wasn't just an explosion, but a fork in the temporal road, sending two entire universes on their separate, opposite journeys through eternity. Imagine the last star in the universe, not exploding in a brilliant supernova, but slowly, painfully, guttering out like a dying candle in an infinite void. For trillions of years, it was the only point of light in a cosmos gone dark. And now it's gone. What happens to time when there's nothing left to light the way? We've journeyed from the dawn of time to the complexities of the present moment. But every story has an ending, and the story of time itself is the most epic of all. So, let's stare into the abyss and ask the ultimate question. How does it all end? The most likely, and perhaps most haunting fate for our universe is something cosmologists call the heat death. It's not a fiery apocalypse, but a slow, creeping, and inevitable decay into cold, empty blackness. You see, the second law of thermodynamics is the universe's most stubborn rule. It states that entropy, or disorder, always increases. Right now, the universe is full of hot spots and cold spots, dense galaxies and empty voids. This difference allows for work, for life, for things to happen. But as the universe continues to expand, everything spreads out. Galaxies will drift so far apart that they disappear from each other's view. Stars will exhaust their fuel and die, becoming cold, dead remnants like black dwarfs and neutron stars. Even the supermassive black holes at the center of galaxies will eventually evaporate over unimaginable timescales through a process called Hawking radiation. Eventually, after trillions upon trillions of years, the entire cosmos will reach a state of maximum entropy, a uniform, featureless soup of subatomic particles at a temperature just fractions of a degree above absolute zero. It's a scenario known as the Big Freeze, where time becomes meaningless because, for all intents and purposes, nothing will ever happen again. But the slow fade of the heat death gets even more bizarre when you consider the ultimate fate of matter itself. This brings us to a mind-bending possibility known as proton decay. We think of protons, the fundamental building blocks of atomic nuclei, as being eternal. But some grand unified theories of physics suggest they aren't. They predict that protons have an incredibly long but finite lifespan. Over a period of at least 10 to the power of 34 years, that's a 1 with 34 zeros after it, protons can spontaneously decay into lighter subatomic particles, like positrons and pions. Think about what that means. Every object, every dead star, every planet, every last speck of dust that survived the Big Freeze would eventually dissolve. It's the ultimate erasure. Matter itself would cease to exist, leaving behind nothing but a thin, cold mist of radiation adrift in an ever-expanding, eternal darkness. It's a level of cosmic finality that's almost impossible for our minds to grasp, where the very substance of reality unravels, particle by particle. Of course, a slow, cold death isn't the only option on the menu. What if the universe decides to go out with a bit more drama? Some physicists theorize a far more violent end known as the Big Rip. This scenario is driven by the mysterious force we call dark energy, which is responsible for the accelerating expansion of the universe. In the Big Rip model, dark energy isn't constant. It grows stronger over time. This hypothetical, strengthening dark energy is sometimes called phantom energy. If this is the case, its repulsive force will eventually become unstoppable. First, about 60 million years before the end, it would become powerful enough to overcome the gravity holding our Milky Way galaxy together, flinging all the stars into the void. Then, as the end approaches, the force would escalate catastrophically. Solar systems would be torn apart. In the final minutes, Earth and other planets would explode. In the last tiny fraction of a second, the phantom energy would become so strong it would overwhelm the forces holding atoms and even atomic nuclei together. The very fabric of space-time would be ripped apart. It's a terrifyingly complete annihilation, not a slow fade, but a sudden, universal shredding of reality itself. But let's flip the cosmic coin. What if the expansion isn't forever? What if gravity, the universe's great collector, has the final say? This leads to the opposite scenario, the Big Crunch. In this model, there might be enough mass and energy in the cosmos, including dark matter, that its collective gravity could eventually halt the expansion and pull everything back in. Galaxies would stop racing away from each other and begin hurtling back toward a central point. The universe would grow hotter and denser as it collapsed. The cosmic microwave background radiation would heat up from a frigid 2.7 Kelvin to a searing blaze, cooking planets and stars. Eventually, galaxies would merge, stars would collide, and everything would be compressed back into the primordial, super-hot, super-dense singularity from which it all began. Time and space, as we know them, would cease to exist in an ultimate cosmic implosion, a perfect reversal of the Big Bang. A final crunch sounds pretty final, but what if it's not an end but a reset button? This is the core idea behind the Big Bounce, a fascinating theory that turns the end of time into the beginning of a new one. In this cyclic model, the Big Crunch doesn't just end in a singularity. Instead, as the universe collapses, quantum forces kick in at the last moment, preventing a total collapse and causing it to bounce back, triggering a brand new Big Bang. This would create a new universe with potentially new physical laws that would expand, live its life, and eventually collapse again, initiating another bounce in an endless cycle of cosmic death and rebirth. Our universe could be just one in an infinite series of universes that have existed before and will exist after. It suggests that time isn't a line with a beginning and an end, but a circle, forever repeating its grand cosmic story. These scenarios paint a picture of time on the grandest possible scale, but they also force us to confront a deeply philosophical question about time's fundamental nature. Let's go back to the heat death, the cold, quiet end. If the universe reaches a state of perfect equilibrium, where all particles are evenly distributed and nothing changes, does time still exist? We perceive time as the progression of events, the measure of change. A ticking clock, a beating heart, a planet orbiting a star. These are all processes. But in a universe at maximum entropy, there are no processes. There is no change. So, has time stopped? Or has it simply become meaningless? It suggests that time isn't a fundamental backdrop to reality, but an emergent property of a dynamic, changing universe. In the absolute quiet of the end, time itself may fade away just as surely as the last star. And it's in that endless, quiet future that we find perhaps the most unsettling idea in all of cosmology, the Boltzmann brain. This is a paradox that emerges from the math of a universe in heat death. In an infinitely old, chaotic system at equilibrium, random quantum fluctuations will still occur. Given an almost infinite amount of time, a near infinite number of these fluctuations will happen. And by sheer statistical probability, it's not impossible that one of these fluctuations could spontaneously assemble particles into a complex, functional object. An object like, for instance, a fully formed human brain, complete with a lifetime of false memories, that pops into existence for just a moment before dissolving back into the void. The paradox is this. In some cosmological models, the timescale for the universe to reach heat death is so vast that it becomes statistically more likely for a conscious observer like you to be a random Boltzmann brain than it is for you to have arisen through the billions of years of organized evolution in the early universe. It's a terrifying thought that destabilizes our entire sense of reality, a final, ghostly whisper from the very end of time. We've journeyed through the cosmos, dissected the atom, and traveled back through millennia, all in a quest to understand time. We've learned that it's relative, that it can bend, and that it might not even be fundamental. But after all that, we come to the most profound battleground of all, the few inches between our ears. Because what good is knowing how time works for a black hole if we can't even control how it feels during a boring meeting? So, how do we master time? The secret isn't in a faster spaceship or a better clock. It's in understanding the software of our own minds. Let's start with a feeling you know well. You're driving down a familiar road, and suddenly a deer jumps out. The entire event might last 2 seconds, but in your memory, it unfolds in glorious, terrifying slow motion. This isn't just your brain being dramatic, it's a documented phenomenon. Our 91st amazing fact is that your brain deliberately stretches time during novel or threatening events. It's called the oddball effect. When your brain encounters something unexpected and important, the amygdala, your brain's threat detection center, kicks into high gear. It commands the rest of your brain to start recording memories with incredible density and detail. Because more data is being encoded per second, when you play that memory back, it feels like it lasted much longer. Your internal clock isn't just ticking, it's a dynamic recording device, changing its frame rate based on how important it thinks the moment is. It's a survival mechanism that ensures you remember exactly how you avoided that deer, turning a fleeting moment into a lasting lesson. But just as your brain can stretch time, it can also make it vanish completely. And this brings us to our 90-second fact. The psychological state of flow is one of the few human experiences that can make our perception of time almost entirely disappear. Coined by psychologist Mihaly Csikszentmihalyi, flow is that magical state of being in the zone. Whether you're a painter lost in your canvas, a coder deep in a complex problem, or an athlete perfectly in sync with the game, you felt it. During flow, your prefrontal cortex, the part of your brain responsible for self-consciousness and time tracking, partially deactivates. This quieting of your inner critic and clock watcher allows you to become completely absorbed in the task at hand. You're so immersed, so challenged, yet so capable that hours can feel like minutes. It's the ultimate paradox. By focusing with absolute intensity on the present moment, we effectively escape the passage of time altogether. It's proof that the most powerful time machine we have is deep, passionate engagement. If losing time in flow is one side of the coin, what's the other? How can we make time feel more abundant? Our 93rd fact shows us how, by actively seeking out awe. Studies from Stanford University have revealed that experiencing awe, that feeling of being in the presence of something vast that transcends your understanding, like gazing at the Grand Canyon or staring up at a star-filled sky, measurably expands our perception of time. When subjects in experiments were exposed to awe-inspiring videos, they reported feeling like they had more time available, were less impatient, and were more willing to volunteer their time to help others. The theory is that awe forces us to slow down and reevaluate our place in the universe. Day-to-day worries and deadlines seem petty in comparison, and this shift in perspective makes time feel less scarce and more plentiful. So, if you want to feel richer in time, don't try to save minutes, go find a moment of awe. This leads directly to one of the great temporal mysteries of modern life, our 94th fact, the holiday paradox. Why does a week-long vacation feel incredibly inexpansive while you're living it, but when you look back, it seems to have flown by in an instant? It's a direct clash between two of the principles we've just discussed. While you're on vacation, you're constantly experiencing new things, new sights, sounds, and foods. This is the oddball effect in action. Your brain is in high-density recording mode, creating rich, detailed memories that each day feel full and long. But when you get home and look back, your brain assesses the duration based on the span of the memory, which is just 1 week of vacation. It gets filed away as a single event. In contrast, a routine week at work feels like it flies by in the moment because there are no new stimuli, but looking back, each distinct, boring day can make the week feel like a long slog. This internal tug-of-war isn't just in our heads, it's embedded in our cultures. Our 95th fact is that entire societies operate on fundamentally different concepts of time. Anthropologists divide cultures into two main groups, monochronic and polychronic. Monochronic cultures, like those in the United States, Germany, and Japan, view time as a finite, linear resource. It can be saved, spent, wasted, or managed. Schedules are sacred, punctuality is a virtue, and tasks are completed one at a time. Polychronic cultures, common in Latin America, Africa, and the Middle East, see time as fluid, cyclical, and open-ended. Relationships and social interactions are prioritized over rigid schedules. Punctuality is less important than the quality of the human connection, and people are comfortable juggling multiple tasks and conversations at once. Neither is right or wrong, but it demonstrates that the ticking clock we take for granted is not a universal truth, but a cultural invention. The pressure of that monochronic clock can have some serious consequences, which brings us to our 96th fact: time pressure literally makes us dumber. Neuroscientists have found that when we feel rushed, our brains switch from the thoughtful, analytical prefrontal cortex to the more primitive, reactive parts of the brain. We suffer from cognitive narrowing, or tunnel vision, where we are less able to see alternative solutions or consider long-term consequences. We're more likely to rely on stereotypes, make impulsive choices, and commit simple errors. This is why cramming for an exam is so ineffective. You might be able to shove information into your short-term memory, but you're not forming the deep, flexible neural connections needed for true understanding. The feeling of not having enough time is one of the biggest barriers to creativity and intelligent decision-making. The best way to solve a complex problem is often to create an environment where time pressure feels absent. So, how do we fight back? How do we create that feeling of spaciousness? Our 97th fact points to an ancient practice with modern scientific backing: mindfulness meditation. Neuroimaging studies have shown that regular mindfulness practice can physically alter the brain regions associated with time perception, particularly the insula. By focusing on the breath and bodily sensations, practitioners become acutely aware of the present moment. This practice essentially trains the brain to perceive time in higher resolution. Experienced meditators report that moments seem to stretch out, allowing them to perceive more detail within a single second. It's the neurological equivalent of upgrading your internal camera from 24 frames per second to 120. It doesn't slow down external reality, but it enhances your ability to process it, creating a subjective feeling of having more time and greater control over your reactions. This idea of different qualities of time isn't new. The ancient Greeks had two distinct words for time, giving us our 98th amazing fact. The first was chronos, which is the root of chronological. This is the time we know all too well, the quantitative, marching, unstoppable sequence of seconds, minutes, and hours. It's the time of clocks and calendars. But they had another word: kairos. Kairos represents qualitative time. It's not about the duration, but about the moment itself. The opportune time, the right time, the decisive moment for action. Chronos is when the train is scheduled to leave. Kairos is the split-second decision to leap aboard as the doors are closing. While our modern world is utterly obsessed with managing Chronos, we've largely forgotten the art of recognizing Kairos. Mastering the moment isn't about scheduling every second. It's about cultivating the awareness to see and seize those fleeting windows of opportunity, inspiration, and connection that truly define a life well lived. We've journeyed from the dawn of everything through the strange loops of relativity and into the ticking machinery of our own minds. We've seen time stretch, shrink, and nearly break. Now we stand at the edge of the abyss, looking into the final, unfolding mysteries. We've counted down dozens of facts, and we're about to explore the last and perhaps most profound truths about the one thing we can never get back. Because after all this, we have to ask, is our own perception of time even real? Let's start right there, inside your head. You see, your internal clock is a fascinatingly flawed instrument. We call this sense chronoception, and it is wildly inconsistent. It's not a steady metronome. It's more like a jazz drummer, speeding up and slowing down based on your emotions, your age, and even your body temperature. When you're frightened or in an accident, your amygdala, the brain's alarm center, kicks into overdrive, creating denser, richer memories. Later, when you play those memories back, they feel longer because there's simply more data packed into them, creating the illusion of slow motion. Conversely, as we age, time seems to accelerate. This might be because, for a 10-year-old, a year is 10% of their entire life, a huge chunk. For a 50-year-old, it's a mere 2%. New experiences also slow time down, while routine makes it fly by. This is why childhood summers felt endless and why your last month at work might feel like a blur. Your personal timeline isn't written in ink, it's written in the fickle language of your own biology. This biological perception of time is, of course, limited to life as we know it. But what if, on a cosmic scale, time isn't just something to be perceived, but something to be consumed? It sounds like science fiction, but it's the basis of the chronovore hypothesis, a speculative idea that some cosmic mysteries could be explained by hyper-advanced civilizations feeding on time itself. The theory suggests that a sufficiently powerful intelligence wouldn't just need matter or energy, but might find a way to manipulate space-time to harvest energy from stars across their entire lifespan, essentially eating their timeline. To us, such an act might look like a star dimming inexplicably, like the bizarre behavior of Tabby's star or other cosmic anomalies we can't explain. Are we just seeing the cosmic leftovers of a civilization that treats stellar life cycles as a casual snack? It's a wild, unproven idea, but it reframes the silence of the universe not as emptiness, but perhaps as evidence of beings operating on a temporal plane we can't even begin to comprehend. And if you think manipulating time is pure fantasy, well, modern physics has a surprise for you. We've discovered a new phase of matter that does something impossible, something that breaks the fundamental symmetry of time. Meet 96 time crystals, a state of matter whose atoms repeat a pattern not just in space, like a normal crystal, but in time. Imagine a diamond with its atoms locked in a perfect repeating lattice. That lattice is stable, it doesn't move. A time crystal, however, is different. Even in its lowest energy state, what's known as its ground state, its atoms are in constant, periodic motion, flipping back and forth in a repeating cycle without using any energy. It's like a clock that runs forever without ever needing to be wound. These aren't just theoretical, they've been created in labs. Time crystals won't lead to time travel, but they represent a fundamental crack in our understanding of time, proving that it can have a physical, repeating structure, just like space. The universe, it seems, can keep its own perfect time. But what does all that time get us? In a universe that is 13.8 billion years old, with trillions of galaxies, we are seemingly alone. The Fermi paradox, the eerie silence where cosmic neighbors should be, is one of science's greatest puzzles. And one of its most chilling potential answers involves time. This is the idea of the Great Filter, a theory that suggests some barrier prevents life from reaching an advanced spacefaring stage, and that time itself may be the filter. Civilizations might emerge, thrive, and then inevitably destroy themselves through war or environmental collapse. Or perhaps the cosmic timescales are just too vast. A civilization might broadcast signals for 1,000,000 years, a blink of an eye in cosmic terms, and we just happen to be listening in the wrong billion-year window. The universe might have been teeming with life 1,000,000,000 years ago, and it might be again 1,000,000,000 years from now. Perhaps we are just born at the wrong time, living in the quiet moment between cosmic symphonies. This forces us to look ahead, to the ultimate timeline of the universe itself. What is the grand finale? What happens to time when everything else is gone? The truth is, we don't know, but the theories are spectacular. The ultimate fate of the universe dictates the ultimate fate of time's arrow. The leading theory is the heat death, where the universe continues expanding until every star has burned out and every black hole has evaporated, leaving a cold, dark, and perfectly uniform soup of particles where nothing ever happens again. In this state, the arrow of time would become meaningless. With no change, no entropy, could time even be said to exist? Another, more violent possibility is the Big Rip, where the accelerating expansion of the universe becomes so powerful it tears everything apart. Galaxies, stars, planets, and eventually the very atoms and fabric of space-time itself. A third, now less likely theory is the Big Crunch, where gravity eventually wins, pulling everything back into a single point, potentially triggering another Big Bang. in an endless cycle of cosmic death and rebirth, where time itself might be reborn again and again. But let's stick with that quiet, cold, endless future of heat death for a moment. Because in that infinite expanse of time, something truly strange could happen. This leads us to one of the most unsettling ideas in all of physics, the Boltzmann brain paradox. This thought experiment proposes that in an infinitely old, dead universe, over unimaginable timescales, random quantum fluctuations could, by pure chance, assemble particles into a complex structure. And given infinite time, it is statistically far, far more likely for a single, fully formed human brain, complete with a lifetime of false memories, to pop into existence for a brief moment than it is for the entire, low-entropy, orderly universe we see around us to have formed from the Big Bang. This means that you have no way of proving that you aren't a Boltzmann brain, a fleeting consciousness that just flickered into being in the distant future, complete with fake memories of watching this very video. It's a terrifying, logic-bending paradox that uses the sheer scale of time to undermine our very sense of reality. And maybe that's the final lesson. After all of our measurements, our theories, our clocks, and calendars, the final, most mind-altering fact about time is this: the present moment as a single universal now simply does not exist. Einstein's relativity proved it. Because the speed of light is finite, when you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the Andromeda galaxy, you're seeing it 2.5 million years in the past. There is no way to synchronize all the clocks in the universe to a single shared now. Your now is unique to your position and motion. My now is different from yours, and both are different from the now of someone in another galaxy. We are all living in our own personal time slice of the universe. The past, present, and future are not a universal river we all float down together. It's a vast, four-dimensional block of space-time, and we are just experiencing our own unique path through it. So what is time? It is the flaw in our memory, the engine of the universe, and the space between heartbeats. It is a cosmic mystery being consumed by imaginary aliens and a physical crystal sitting in a lab. It is the silent filter of the cosmos and the source of a paradox that questions our very existence. From the first fact to the 100th, our journey has shown us that time isn't just a number on a clock. It is the ultimate context for everything. It is the canvas on which our lives and the life of the entire universe are painted. And our brief, beautiful, fleeting moment to witness it all is happening right now. For you.